Okay, so now let's revisit the one password again. So we consider the possible models for KB, assuming only pits and a reduced one password. So initially, the agent is in square 1, 1. Then it chooses to move to square 2, 1 and perceives brace in this square. So currently, the perceives combined with the agent's knowledge of rules of the one password constitute the KB. Okay. So now the agent is interested in whether the adjacent squares 1, 2, 1, 2, 2, 2, and 3, 1 contain pits or not. So each of the three squares might or might not contain a pit. So there are 8 possible models in all. Okay. So as shown in this slide, these are all possible ways to fill the question marks in this left subfigure. Okay. Take this state, for example. There's no pit in each of these three squares. Now this state means the pit is in square 2, 2. Now this state means all these three squares have pits. We have mentioned that the knowledge base can be sort of a set of sentences. The KB is forced in models that can contradict what the agent knows. So we mentioned again, the KB is a set of sentences. So the KB is forced in models that contradict what the agent knows. Okay. For example, the KB is false. The KB is false in any model in which 1, 2, the square 1, 2 contains a pit, because there's no brace here. Okay. So moreover, there should be a pit in either square 3, 1 or 2, 2 or 2, 2 or both, because there's a brace in this square. So the KB includes these three possible words, which is surrounded by red line in this figure. Okay. So we need to determine the models of KB. So firstly, pit is not in square 1 2 square 1 2. So this is not the model of KB. This is not. This is not. This is not. Okay. And the second one, there should be pit in square 2 2 or square 2 square 3 1 or both. So this is also not the model of KB. So the model of KB includes these 3 states. So I use the red line to denote the KB, the model of KB. Okay. So based on this knowledge base, based on this KB, the agent will know that square 1 2 is safe, because in all models of KB, the square 1 2 has no pit. Okay. Then the agent go back to square 1 2. Go back to the agent will go back to from 2 1, go back to 1 1, and then go to 1 2. Okay. So if we use alpha 1, to denote the square 1 2 is safe. So what models does alpha 1 have? So we need to determine the model of alpha 1. Now we can find in all these 4 states, there's no pit in square alpha 1. Alpha 1 is okay, because so they are the models of alpha 1 surrounded by this yellow dotted line. Denote the models of alpha 1, which includes these 4 states. So now we can find the model of KB is actually a subset of models of alpha 1. So this holds. So this is equivalent to KB entails alpha 1. So we have this. So this is completed by model checking. That is, we checking the models of these 2 sentences. These 2 sentences means the sentence KB and the sentence alpha 1. We compare the models of these 2 sentences. Okay. Now if we use alpha 2 to denote that the square 2 2 is safe. So which is the models of alpha 2? Now we can find in these 4 states the alpha 2 are okay. Only these 4 states the square 2 2 is safe. So this corresponding to the model of alpha 2. Okay, which is denoted by this red dotted line. Is M alpha 2. Now we can find the MKB is not the subset of M alpha 2. So we cannot conclude that alpha 2. So KB doesn't entail alpha 2. Okay. So in the last of this section, we introduce some concepts in logical inference procedures. So if an inference algorithm I can derive alpha from KB, so we can write as this, which is pronounced alpha is derived from KB by I. Okay. The following two concepts are soundness and completeness. So what does soundness mean? An inference algorithm that derives only entailed sentences is called sound or truth preserving. Okay. So soundness is a very desirable property in logical inference. It aims to get no wrong inferences, but maybe not all inferences. The model checking we used before is a sound procedure. Okay. The property of completeness is also desirable. So the definition of completeness is an inference algorithm is complete if it can derive any sentence that is entailed. So it means that all inferences can be made, but maybe some wrong ones as well. Okay. In the following contents of this chapter, we will come to describe the propositional logic. So we will get some deep understanding to the soundness and completeness, these two properties. So these are the contents of today's course. Thank you.